Good afternoon, everybody. Let's get started with the class. For announcements, homework 5 is posted, but that's not due for a little while. I think you have a couple weeks until that's due, so that'll be due on October 30th. The homework or the lab session 6 or lab 6 will continue this week. So you'll continue your work on sensors. And if you got that lab done and you've demonstrated already, and then you're all done. You don't have to come to lab this week. If you haven't finished your lab, then this is an opportunity to finish up that hardware and that software and get some help from the TA. And so that will continue this week. So during the previous class, we finished up talking about power sources and power conversion. Toward the end of that session, we talked about DC to DC switching converters and linear regulators. We're going to change topics today and move into a new major topic. We're going to talk about microcontrollers for sensing and control. So you're using a microcontroller in lab. The Arduino has a microcontroller integrated circuit on it. There are many other types of microcontrollers of various capabilities. So this is a worthwhile topic to cover because you sense with them, you control with them, you can run control loops like you're doing in lab. You can do many things. Many products have microcontroller integrated circuits or some type of embedded programmable integrated circuit that has a microcontroller essentially on it. So we're going to cover this as part of the electronics that I think mechanical engineers and non-electrical engineers would benefit from having some experience. Okay. All right. So let's talk about microcontrollers and embedded systems. So a microcontroller is typically part of what we call an embedded system. An embedded system has some kind of electronic controller in it. Sometimes it's a microcontroller, sometimes it's a microprocessor. But this is part of the hardware and the software that forms a component of some larger mechanical and electronic system. And usually the embedded system is expected to function most of the time without the need for human intervention. So like your refrigerator, right? Your refrigerator probably has some kind of microcontroller functionality in it. Let's see, it has to have a thermostat, it has to have a light that turns on and off. When you hit the switch, it has to produce ice, things like that. So that's some kind of device that really doesn't require much human intervention. But the processor in the embedded system, the microcontroller or the microprocessor, typically supports the product, but it's not the point of the product. It's not the main reason for having the product. Like think about your refrigerator, right? You don't care that it has a microprocessor or a microcontroller of a certain speed. Think about your PC. Well, you're crunching numbers. Even if you're playing games or running MATLAB, then you typically care about how fast your processor runs, how much memory you have. You don't care so much about your refrigerator having a high processor capability as long as your food stays cold and you get cold water out of it. So products that have sense and control functions probably have microcontrollers in them or some kind of application specific integrated circuit or otherwise an integrated circuit, FPGA maybe, that has some kind of software programmable microcontroller functionality. Many products have that. Your refrigerator, your appliances, your car has pretty complex software going on in there, from running the engine, controlling timing, to controlling the anti-lock brake system. We'll talk a little bit about those sensors later. Okay, instrumentation in all kinds of vehicles and aircraft and machinery. And there are many industrial applications. Processes are controlled by microcontrollers that have sensors coming into the board or the chip in order to get readings of temperature and pressure and all other physical quantities, and then to run to provide outputs to control the system. And microcontrollers span a wide range of functionality and cost, right? So you have I'll call it a medium scale microcontroller on your Arduino board. It's pretty capable though. You can get microcontrollers with much fewer pins, maybe an 8-pin microcontroller that has just a little bit of functionality, but it's extremely cheap. And then you can get very high speed microcontrollers that use more power, have more capability, have many more outputs, are larger, cost a lot more. So, so there's a wide selection when you're trying to match a microcontroller to your application. Typically what I do is I overspecify the microcontroller for a prototype and then try to back down if I don't need so much capability. Okay, so typically microcontrollers have these capabilities in embedded systems. They do this. They have digital input and output. You're using an infrared sensor in your project. So you can connect digital sensors and digital controllers, other controllers, to a microcontroller and communicate digital information. The microcontroller capabilities typically include some kind of analog input and output. So you can take in an analog signal, represent that analog signal with a range of binary numbers, and then react or do something with that input. You can also typically produce an output from a microcontroller, either using pulse width modulation, like you're doing in lab, or some microcontrollers have digital to analog converters built in. Or you can use an external digital to analog converter to produce an analog signal and analog voltage from software. Okay, microcontrollers typically have some kind of timing capability where you can run timers to time very close events, maybe microseconds apart or milliseconds apart, or even hours apart. It doesn't matter. But these timers let you time when events happen. And they also let you produce waveforms like your pulse width modulated waveform that you're producing in lab, or using timers. So that's another useful function. Microcontrollers microcontrollers also have peripherals that enable communications. So like serial port communications, like SPI, serial peripheral interfaces, like I2C interfaces to communicate either between sensors and the microcontroller, or between microcontrollers, or even between systems outside of your system to another system. So they typically have this capability, all built in to a tiny package that you can put into your product or project or research. All right. Okay, so uh, let's talk purpose and applications. So the microcontroller is the integrated circuit, typically used to sense or measure physical quantities and to output some kind of signals that provide control. Right. So this is a microcontroller. In fact, I think this is the one on one of the Uno boards, the Arduino Uno boards. So we often call the board the microcontroller. I guess strictly speaking, we should call the chip or the integrated circuit the microcontroller, and then the microcontrollers surrounded by supporting electronics that provide a clock signal to synchronize events, and maybe some communication peripherals and a voltage regulator, things like that. Okay, but that's the microcontroller to sense and control. And contrast a microprocessor. Microprocessors typically used to process data, to crunch data, to run calculations at, well, hopefully high rates, because you usually want your answer right now. Microcontrollers, though, although they're slower typically, they generally have more peripherals than microprocessors. And this lets it support sensing and control. So even though they're a little slower, often, it doesn't have to be, but often they're slower, you usually don't need that processing power. You usually want maybe many more channels of analog to digital conversion, or many more digital ports, something like that. And microprocessors have fewer of those typically. They both, though, have software definable logic functions. Okay, so you can program in combinatorial logic, sequential logic, branching. You can do some pretty complex software these days in even simple microcontrollers. And what you usually do is you use a PC to create software. You write the code, often in C code, like we're doing in lab. You compile that code and you download those instructions in a format that the microcontroller can execute. You download that into the microcontroller's program memory. Okay, and then the program can run once the microcontroller is powered up. So microcontrollers have many capabilities, more than we could possibly go through in detail, even if we took the whole semester, I would claim. There would still be a lot of side reading. For example, the common Atmega 328P, this is the chip. I think this one's on the Uno, one of the original versions. You have the Wi-Fi version. That's a different chip. This is one of the original Unos. Um, you've seen data sheets for an op amp or an LED or a transistor, which are a few pages. Microcontrollers often have uh, data sheets that can be 100 pages or hundreds of pages because they have so much capability that they can implement. For example, this microcontroller, the simple Uno microcontroller, has a 294-page data sheet describing what it can do and how to use those capabilities. And so what I usually do is I'm usually looking for a specific capability, maybe an analog to digital converter, maybe a pulse width modulating generator, and I go look at those chapters, right? You got to read some of it. That's common, but they're pretty hefty data sheets. Don't let that intimidate you, because oftentimes you can get the microcontroller up and running, and then only when you want specific capabilities, timers, timing events, you can go to those sections of the data sheet. So this is a dual inline pin package of a microcontroller. They come in many different form factors. Here's a surface mount microcontroller that has many more pins on it, right? And here's another surface mount microcontroller. The pins are underneath along the edge. So they come in many different packages, many different physical sizes to integrate into your circuit board or to use on a development board. Okay, so I took the topics that I think we want to dig into based on what I think are the most useful functions of a microcontroller and the most useful concepts. So here are the typical and what I consider the most important microcontroller concepts and functions of a microcontroller and peripherals built into the microcontroller. Okay, so first is the microcontroller hardware. So we're going to talk about the integrated circuits and the development boards and show a little bit about those. And then we're going to talk about digital signaling and number systems. We're going to talk about binary and hex because you have to have a handle on those when you're setting configuration bits in the microcontroller. For example, to make a port a digital port or to make a pin an analog to digital converter, you've got to understand binary numbers and hexadecimal too. Oftentimes in the C code, we're using hexadecimal, which is base 16. So that's just a quick review of that. We're going to look at the Arduino IDE because you're using that in this class. But in talking about that, that also applies to other IDEs. This is an integrated development environment. IDEs typically have some kind of editing tool, like a text editor built in. They typically have some kind of file browser and file tree. They typically have a compiler that can either internally or called by the IDE. So we'll talk about that. The Arduino IDE is a really integrated IDE, so you don't have to do much to configure it. It just works out of the box usually. But there are many other IDEs out there. We'll talk about digital ports for logic signal input and output. So for example, when you're sensing the blade crossings in your project using the infrared detector, that's a digital input. Digital ports can also output values, output high values and low values to control, like your motor. You can turn your motor on and off with a digital port. If you turn that digital port into a pulse width modulation output, you control the speed like you're doing. So we'll dig into that a little bit. We're going to talk about analog to digital converters, some of the details there. for analog signal inputs into the chip. We'll talk a little bit about interface circuits. So when your voltage that you're trying to sense doesn't exactly match the range of the ADC input, well, what do you do about that? Okay, that's an important topic to get the best resolution of a measurement by the microcontroller. We're going to talk about timers for event capture and waveform generation. So we'll talk about how the timers work. They're basically counters that run at a specific rate. You can control a scaled version of that rate of that counter. And we'll talk about waveform generation, like pulse width modulation, and how timers are used to generate the waveforms you're using in lab. And then if you're deviating from what we're doing in lab for your own project, well, how do you create your own pulse width modulated signal with maybe different frequencies and different duty cycles? So this will give you some insight into how that works. And then we'll talk about interrupts. And so interrupts, we talked about this a little in lab. Interrupts allow you to execute functions that maybe don't normally execute when an event happens. Like in lab, every time the propeller blade crosses in front of the light detector, right, the infrared detector, that signals a blade crossing, and we want to time that event so we can sense RPM. So there's an interrupt function with an interrupt service routine that immediately captures the microsecond level clock so that you can time when the blades cross and time between blade crossings and calculate RPM. So you can do this. You can use interrupts for a lot of different functions. Respond to communication signals, respond to different conditions, respond to even timers. Okay, and finally, we'll talk about guidance for writing microcontroller software. So some good practices there. So I think this is the 80% solution, right? So if you have to learn microcontroller topics in a finite amount of time, I think these are they. So these cover, I think, 80% of what you need. And for your control and your sensing applications. And I think this will give you enough background to continue into other microcontroller and microprocessor topics, right? If you want to go learn more once you have this kind of basis from which to work, then you can dig into digital to analog converters or SPI communications, SPI communications. Having this knowledge, you will understand the vocabulary, be able to speak in binary number systems, and have some background in some of the peripherals. All right. Okay, so since we're using the Arduino in class, let's talk about the Arduino and Arduino-based boards. So this is a very popular microcontroller platform. Hobbyists use it a lot because it's cheap, has a lot of free tools. So if you're a hobbyist or an experimenter, it's a good microcontroller to use. But even many professional rapid development projects can use the Arduino as a prototype controller. Typically you might even use the chip on your custom circuit board, but early it's often very fast to take a development board, program in sensing and control into it, do a demonstration, and then later create a custom board. So the Arduino is pretty good for that. So when we say Arduino, it's really a family of development boards, right? So you're using the Arduino Uno Wi-Fi Rev 2 board. And many of these development boards use the Atmel microcontroller, which was purchased by, Atmel was purchased by Microchip, which is a company, like the Atmega 4809. But I think actually other microcontrollers are being used now. So not that it matters a whole lot, but you can look at the particular board and check out the capabilities and look at the data sheet, and you can figure out what kind of microcontroller is being used. But they've become really popular because there's a huge community of users, amateur and professional. It's an easy development environment to use, as you've seen. Some glitches. We had some glitches, but pretty much it works, and it's fairly straightforward. There's open source hardware and software. So that means for the software, you can go look at the libraries, and you can go look at the code. And for hardware, you can get the schematic of this development board, and you can use sections of that in your own project. And there's a huge amount of support on the web. So if you need to know how to do something with this board, someone probably has done it, and you can find an explanation. You might even find some template code and and get it for free a lot of times. And the boards are fairly cheap. You can get them from, a few bucks up to, I think the board we're using is about maybe around $50, but it's got built-in Wi-Fi and um, a lot of built-in peripherals in it, and an IMU, an inertial measurement unit. So it's a pretty neat little board. So and Arduino programming resources now support other microcontrollers. So there's some Wi-Fi modules out there. You can use the Arduino IDE to program these Wi-Fi modules and set up a sensor network for your project. And they're pretty easy to use. So it's a nice ecosystem of hardware and software for a project or to get started on a prototype. Okay. Okay, so here's an example. This is the board you're using, the Arduino Uno Wi-Fi Rev 2. Let's take a look at the board. So here is the Atmega 4809 microcontroller. So this is the microcontroller right here. That's really it. Everything around it is supporting that microcontroller, either like a voltage regulator or sensors or LEDs or a USB communicating chip, or it's all supporting around it. And this microcontroller is on this, eval board, development board, whatever you want to call it. And that gives you easy access through headers to get to the signals from the microcontroller and peripherals. So this is the external power input. If you don't want to have this board connected to your computer all the time, because normally you plug the board into your computer using the USB port and the board powers up. If you don't want a computer there, you can program the program memory of the microcontroller, disconnect it from the computer, and then apply external power, and the board will run. Right? There's a voltage range you can find in the Arduino datasheet. Okay, there's a step down converter. This is a buck DC to DC converter here, a 5-volt converter. So there's a chip right there. That's what we talked about during the last lecture. So there's a whole DC DC converter in a chip with I'm sure some surrounding components there that make it work. Okay, here's a linear voltage regulator. You're going from some higher voltage to some linear or some lower noise voltage using this linear voltage regulator, 3.3 volts. So now you should know what each of these is, right? DC to DC converter and a linear regulator. Here are the power supply noise filtering capacitors. There, right? We've talked about those decoupling capacitors, filtering capacitors. This is a 16 megahertz clock crystal oscillator. So when you're talking clock speeds, you're probably used to talking in the gigahertz range for PC microprocessors. And here you're talking megahertz, 16 megahertz, but that's often fast enough to do what you want to do. A clock oscillator crystal is part of a clock oscillator that creates a square wave, and events happen in the microcontroller, usually on edges of the square wave or divided down edges of that square wave, meaning at a lower rate. All right, here's the USB programming and power interface. That's not on all microcontroller development boards. It's very convenient here. Oftentimes, when you have a microcontroller board, you have to connect it to a programmer, and that programmer converts from USB to the signals that can program the memory in the microcontroller and run debug functions. So this is a very convenient function peripheral to have on this board. This is the USB interface integrated circuit here. So something has to talk to your computer, and then something has to convert what you're sending, that object code, to send it into the microcontroller's program memory. You have headers, the top and the bottom here in this picture. So that just gives you access to the microcontroller pins. You can see the digital ports here, right? These are the digital ports, 0 through 13. These numbers don't necessarily correspond to the digital port numbering of the microcontroller. So Arduino defines their own pin numbering for the board, not the controller. But you can see you have access to ground here. This AREF, this is what we talked about in lab. This is the analog to digital converter reference voltage. We'll talk about that later, but you can actually apply an external reference voltage if you don't like the voltages that are provided inside the microcontroller and programmable to different levels. Let's see. So down here you have analog to digital converter inputs right here. Here's some power. There's ground, 5 volts, 3.3 volts. So those voltages are associated with these converters and the regulator over here. Okay. And so you have access to the pins of the microcontroller, the ports, and power. This is probably the input voltage from the external power input here. Okay. This is the Wi-Fi module. So the chip itself does not have Wi-Fi. The microcontroller doesn't have Wi-Fi, but the board has this module that communicates with the microcontroller. And so you can see this is a whole module integrated here, and then this little slot here is the antenna. Okay. And this is a cool feature on this board. This is the inertial measurement unit. It gives you a 6 degree of freedom accelerometer and gyroscope. That means XYZ acceleration. You can see the axes written here. So XYZ acceleration and gyroscopic rates around the X, Y, and Z axes. Okay, so that's what I mean. This is the microcontroller. This is the microcontroller board. Some people call this just the microcontroller, but it has a lot of peripherals on it, and there has to be a lot of not a lot, but there have to be some electronics surrounding it, like the voltage regulators and any peripherals that you want to use for programming or sensing. Okay, there are many different board types, so I'll just show you a few here. This is the classic Arduino Uno, right? It's low cost, it's medium size, it's easy to get access to the pins, it's easy to program, you can apply external power, but it's relatively large size for what it needs to be. It uses this Atmega 328P microcontroller, right? You're using the Atmega 41 or 4809 on your board. But if you need a smaller board, you can go to something like the Arduino Nano, and here's the microcontroller, and you can solder some pins into those header holes there, right? It doesn't have the nice sockets that you can plug breadboard wires in, but if you need a smaller footprint, you can use one of these that has a smaller USB connection on it. So that's nice. If you're going to go fly something on a drone or do something like that, you might want a lighter board. And then if you need a lot of input and output and higher processing power, here's the Arduino Giga R1 Wi-Fi. So it's high computing power relatively, and a large number of input and output pins, right? So if size isn't a consideration, or you can fit this and you need a lot of processing capability and a lot of ports, you can use this. This is a cool little board. You can pick these up really cheap, and they enable you to connect an Arduino compatible processor, microcontroller, to Wi-Fi, all in one little board here, and program it with USB. Okay, you can pick these up for, I mean, they're $5 a piece or less. So you can build a whole sensor network in your home or in your project. And then this was big for a while. I think they're still used, but the shields for the Arduino Uno. So these circuit boards fit on top of this board, on top of the Uno board. So you can add Ethernet, or you can add relays if you need to control some DC circuits, or you can add a motor driver without having to build one yourself. So microcontroller development board options, they really do span a wide range of sizes and speeds and peripherals capabilities, pinouts, the number of pins, the number of ports you have access to, and power consumption. So if you're running, if you're running something that has to be on a couple AA batteries for a while, um, you might consider one of the smaller, lower power, lower computing boards compared to one of the higher computing boards if you don't need that kind of processing power. Okay, let's take a look at, well, a microcontroller integrated circuit, right? The one you're using in lab. Here is a block diagram. Okay, so let's see what we see here. So inside, here's the dotted line. You can see we have the connections to the outside. You have the central processing unit. The CPU executes instructions. It's what performs the calculations, and it controls all of these peripherals. This is an 8-bit CPU. So you know how you download software and it asks you, do you want to download the 64-bit version of the software for 64-bit Windows? Well, this is actually an 8-bit microcontroller that works on an 8-bit bus. So here is flash memory. Flash memory stores instructions, and that's the program that you write to execute. There's 48 kilobytes in here. And so flash memory can be programmed once, and you can remove power. And if you remove the power, the flash memory still stays programmed. Okay, so you can disconnect from a battery, go plug it in again, and your program will run. Notice the amount of memory, 48 kilobytes, right? That's not that much when you're used to talking about gigabytes of memory in PCs. But usually these programs that you run in microcontrollers are not super complex. You can run out of memory. You can get more memory than this, but oftentimes that's enough. Here's electrically erasable programmable read-only memory. This is EEPROM. So this is memory that you can actually write to with your software. So if you want to write a value or write values to memory and then have those stored even when you unplug the microcontroller, then you can put them in EEPROM. Okay, that lets you plug and unplug and store some values. Maybe those are configuration values or last state values, something like that. But notice there are only 256 bytes, not kilobytes, not megabytes, not gigabytes, but 256 bytes of memory in there. This is RAM, random access memory. This is what they call volatile memory, right? Volatile memory means it's memory that goes away when you disconnect the power source. So non-volatile memory, like flash memory, holds on to its memory, but RAM, which is volatile memory, will lose its values when you unplug it from the battery. And there's 6 kilobytes to work with. So when you're storing numbers in variables or arrays, this is where those values get stored. Then we have digital I/O ports. So these are input and output of digital values, high or low values. These also can output pulse width modulation signals. And so each one of these ports, PA, port A, port B, port C, port D, right? You'll see there's a little N if you can read that right afterwards. That's because you can have PA0, PA1, PA2. So each one of those ports actually has 4 or 8 bits, 4 to 8 bits each. So there are many more than just 6 digital values. Some of these are multiplied by 8 bits. Some of these are multiplied by 4 bits. So there's a lot of values you can get to there, input and output. Okay, so here's the clock. This is the clock generator. Here's that clock crystal that I had highlighted on the hardware. that sets the frequency. So instructions are executed on every clock cycle. And this clock typically is running at 16 megahertz. And you can change that. Some of microcontrollers have internal clocks that don't use crystals. They're less precise on their timing. And you can actually provide an external clock. If you have another clock somewhere else in your circuit, you can provide that square wave and synchronize this microcontroller to it. Okay. Here's an analog comparator. So this is a peripheral. This acts like, well, if you took my circuits class, my intro to circuits class, we talked about comparators. They compare two voltages and provide an output high or low, depending upon which voltage is higher. You can use that. You can use op amps and specific comparator chips external to the microcontroller to compare voltages, but this chip has comparators built in. Okay, so you can do comparisons there. Here's an analog to digital converter, and there are several analog to digital converters often on these chips, on the microcontroller chips. So this particular microcontroller samples analog voltages with a 10-bit resolution. So 2 to the power of 10 is the number of levels. So 0 to 1023. And we'll talk more about how that works, but these are all built in to the microcontroller. Okay, here are the timers. So this is for waveform generation or measuring the time between events. And when I say time between events, it can be an event, it can be an external event like pulses coming from a circuit, like the infrared detector, or it can be sometimes internal events that happen, either a interrupt firing or something like that. And this chip has two 16-bit timers. Okay. And then there is serial data communications on this chip. So you can communicate with PCs, you can communicate with other microcontrollers, you can communicate with sensors. I mentioned in lab, so you're using an analog temperature sensor and you're connecting that analog sensor to the analog to digital converter. But there are also similarly packaged temperature sensors that have digital outputs, and they'll just give a number. You power it up and they output, you send it a command and it outputs a number, a digital number, a binary number that you can read with usually SPI or I2C or this two-wire interface here. So so there's some communications built in there. Okay, so that's what you're looking at inside this chip. And so you can dig into the data sheet and read about every one of these internal peripherals and learn how to use them, and then get example code and figure out how to use these to make your project happen. All right. Okay, so let's move on to digital voltage waveforms and binary values. So you probably have worked with these before, but it's worth pointing out some specific values and concepts that sometimes are glossed over. So digital voltage waveforms, I'll call these signals as well, represent numeric data and logic information. So binary signals are restricted to two voltage ranges, representing binary values. That means two level values. And you often interpret these two values as 0 or 1, or off or on, or no or yes, or false or true, right? So if I say, oh, is the output 1 or 0, right? That could also mean high or low, right? So there's lots of different ways to talk about these binary values. But they typically would look something like this. So here's a digital waveform that represents binary values. Okay, so this would be 5-volt logic here. So you might interpret this waveform at regular periods. So each one of these dashed lines. So this is voltage, I should say. This is voltage on the vertical axis. and this is time on the horizontal axis. So this is a voltage that changes high-low over time. And you might interpret uh, a high value as a 1 and a low value as a 0. So this might represent 1010, 1101. Okay. And so just eyeballing this voltage and knowing when to sample the voltage, you can tell should the value be 0 or 1. But you really have to see the data sheet for the microcontroller, or if you're using separate logic integrated circuits, you really have to look at those data sheets for specific logic voltage levels. Okay, so let's take a look at the logic voltage levels for this at mega 4808, 4809 here. So this is just an excerpt from the tables. Okay, so here are two values, VIL and VIH. That means this is the input low voltage. So when an input sees this voltage, it will interpret it as a low or as a 0. When the microcontroller or input sees this voltage, VIH, this range, it'll interpret that as a high, or I would call it a 1. And so let's look at VIL. So we typically think the low voltage is going to be 0 volts, but sometimes it's not exactly 0 volts, depending upon what it's connected to. But if you want the microcontroller to interpret a low, then that voltage at the port input has to be between minus 0.2 volts and 0.3 times VDD. Okay, that's the we say VCC in lab. VCC is common when you're using transistors. If you're using FETs, field effect transistors, this is the drain voltage instead of the CC, which is collector voltage. But nonetheless, this is the power supply voltage to the digital circuit. Okay, and then so between these two voltage levels, between the min and the max, that will be interpreted as a 0, a low. Between these two voltages, 0.7 times VDD or VDD plus 0.2, that will be interpreted as a high, right? And so let's suppose you have a microcontroller power supply voltage VDD equal to 5 volts. Right? That's what you're using in lab. Okay, so what does that mean? That means, okay, for a low, you can go between minus 0.2 and 1.5 volts. So if you have a sensor that is a digital output out of the sensor that is producing 0.7 volts or 1.1 volts, right, it's going to be interpreted as a low. And then to have a voltage interpreted as a high as an input, 0.7 times VDD is 3.5 volts. VDD plus 0.2 is 5.2 volts. So you have to have your voltage in this range to have it interpreted as a 1 or a high value. All right, so you can plot that here. Here's, I just put these voltage ranges. Minus 0.2 to 1.5, that's a low. 3.5 to 5.2, that's a high. So nominally, or with these nominal voltages, you would interpret these values correctly, right? 5 volts is a 1, 0 volts is a 0, right? So that's a 0 and that's a 1. And in between, you shouldn't count on the value, on reading the value or interpreting the value in between. That's for transition only. That's as you go from a 1 to a 0 or from a 0 to a 1, right? You don't want to check the value right there if you're directly sampling the port. Okay, oftentimes there's some buffering in the microcontroller, so you can't get that wrong based on when your software runs. But just to know that in general, you don't want to sample a voltage during the transition from a high to a low or a low to a high. Okay, but this also shows you that if you have a sensor with an output of 4 volts or, as a high and maybe output a half a volt as a low, that it'll still work as a digital source to be read by an input port of this chip. Okay. And so if you have sensors or microcontrollers you want to connect together and they're different logic voltage families, right? If you have to interface, then you would use what are called level shifting circuits. So you can buy chips that are level shifters. You can use FETs in a particular circuit. You can search the web for them to shift between, for example, 3.3 volt logic and 5 volt logic. So that works. In fact, there's some clever circuits that do that in a bidirectional fashion. Okay, so let's talk about rolling up these binary values into words using decimal, binary, and hexadecimal. So it's really common to work in all three number systems when you're programming microcontrollers. You will see all three number systems in code. If you look at my code, you'll probably see it, the template code in lab. You'll see these three different bases. Okay. So decimal is base 10. That's what we're familiar with. And it's probably there because we have 10 fingers and we count on 10 fingers. So when you look at a number like 734, you're really interpreting that number based on the symbol in the digit position and the digit position itself. So when you look at 734 in your mind, what you're really doing, knowingly or not, is you're interpreting 7 as in its position, right? It's in the position 2, digit position 2, 7 times 10 to the power of 2. Plus 3, that's in digit position 1, 3 times 10, 10 is the base 10, right? To the power of 1, its position. Plus 4 times 10 to the 0, its position, right? So that's how we're interpreting 7 in the hundreds place, 3 in the tens place, 4 in the ones place. Binary is changing that to base 2. So computers generally count using on and off states of transistors. And so that's why we like base 2. Binary actually stands, or bit stands for binary digit. And if you take a bunch of binary digits and you put them together in a group, that's called a word. And a byte is a special word. It is an 8-bit word. And when we talk about hex values, we'll actually talk about nibbles, which are 4-bit words. So if you have a 4-bit word that you're trying to interpret in binary, you look at the value, the symbol in that digit. I call it symbol. It's a value in that digit. Its digit position, and you would interpret that value like this. 1 times 2 to the, so 1 in the third digit position here, 1 times 2 to the power of the digit position, plus 1, the value, times 2 to the power of 2, its digit position, plus 0 times 2 to the power of its digit position, plus 1, right, times 2 to the power of its digit position. So 2 is the base. Base 2 is binary. So you get this to be a value of 13. Okay. So 1101 base 2, often I put the base as a subscript, is equal to 13 base 10. So hexadecimal is often used to represent binary numbers using fewer digits. So these two values are the same values here. DF2A and this long string of bits, those actually represent the same value. You could see a prefix here, 0x, that means a hex value follows. And this is a binary value follows 0b. Okay. So DF2A is interpreted like this. Here's counting in decimal. Right, we know how to do that. Here's counting in hex. Hex is base 16. So unlike decimal, which has 10 symbols you can put in a digit, 0 through 9, hex has 16 symbols you can put in a digit, 0 through 9, and A, B, C, D, E, F. So there's 16 there. But you do the same thing. Here is the digit position, right? Here's 13. Okay, so D is a 13. D corresponds to 13 in decimal. This is how to do the conversion. So you have 13D times the base, 16, to the power of the digit position. And then F is 15, right? F is 15 times the base to the power of the digit position 2. And then we have 2 times 16. Here's 2 times the base to the power of 1. And then 10, which is A, right? A is 10. Times 16, the base to the power of its digit position. Okay, so you get this. So you work out that math and you get this is, so DF2A is 57,130 in base 10. Okay. And this convenience actually makes more sense when converting between binary and hex. And this is really why it makes using hex numbers easier in programming. Because if I have this binary number, this is this binary number up here, what I can do is I can convert using 4-bit chunks of this number. I convert each 4-bit word, right? This is 8 plus 2. I can convert each 4-bit word into a hex value, right? 8 plus 2 is 10, which is A base 16. This is 2 base 10, which is 2 base 16. This is 15 base 10, right? 1, 1, 1, 1, 15 base 10, which is an F base 16. And this is 13 base 10, which is D base 16. So I just put those together, and this long binary number is actually DF2A. So it's pretty easy to go between binary and hex by dividing that number, the binary number, into 4-bit chunks and converting. And then in code, you wouldn't have to write 1101111100101010. You wouldn't have to write that. You could just write DF2A preceded by this indicator that says, oh, that's a hex value. Okay. All right. Well, I've gone over on time here. Thank you for bearing with me. I wanted to get through that. So don't forget, homework 5 is posted. So take a look at that. That's not due for another couple weeks though, but let me know if you have any questions. Also check Canvas for the date and time that the assignments are due. That's all posted. I will start office hours in just a couple seconds, so you can stay up on this session if you'd like to join. If not, I'll see you next time. Have a great night.